Hello there, physics fans. Here's another fantastic video describing some of the basic aspects of physics. We're going to start with some basic information for this unit. This video will look at periodic motion overall, what we mean by that term, but then also we'll go over the basic kinematics of uniform circular motion. Here is a list of objectives. The video that you're looking at right now is only going to cover the first three objectives shown in this list. We'll talk about period and frequency, and then how we apply certain kinematics concepts to uniform circular motion. What is periodic motion? Well, I would think that you know the word periodic. You've heard of periodicals. Like a magazine is a periodical. It comes out periodically once every now and then. So periodic motion is something that has a repetitive aspect to it. It keeps happening over and over again. That's what we mean by the word periodic. So periodic motion is anything that repeats. In this unit of study, we're going to be looking at circular motion, which is periodic, but also sometimes periodic. But we can also look later at oscillations of certain types that occur over and over again, like a pendulum. If we are studying those things, we are often interested in the timing. So we have two quantities that we use in science to describe periodic events. And one of them is called simply the period, and the other is called frequency. So you may have heard of these terms before. We can define period as the time for one complete cycle, whatever that occurrence is, whatever it is that's happening. It happens in a certain amount of time, and then it repeats, and that time is called the period. We use the symbol capital T to distinguish it from some arbitrary amount of time. Lowercase t in physics is usually an elapsed time, some arbitrary amount of time. So we use capital T in physics is the most common symbol anyway for this particular amount of time, which has a very particular definition. Of course, the unit would typically be seconds, but could be in hours or minutes, some other units of time. Frequency is not the time for one complete cycle, but rather flip that definition around. Frequency is how often it occurs. That's how many cycles occur per unit time. Students sometimes get these two concepts mixed up, and it's understandable because look at the definitions. They're very similar, but they are flipped around. So try to keep them straight. We're going to look at some examples in this video to help you keep them straight. But frequency is the number of cycles per unit time. The most common symbol would be just lowercase f for frequency. Sometimes you might see the Greek letter nu, but not typically in physics. So most often in physics we'll use f for frequency. The SI unit for frequency is the hertz, named for a scientist. And you might have heard of hertz, as in kilohertz or megahertz, associated with radios and radio stations. Hertz means 1 cycle per second. 1 hertz is equivalent to 1 cycle per second, or simply 1 over seconds, the reciprocal of seconds. Now we're going to do some examples with these concepts in this video. If you want to, pause the video and grab yourself a stopwatch, or just use your cell phone as a stopwatch. And we're going to play around with these concepts. I have a stopwatch here I'm going to use as we look at some examples. So here we have a little smiley face guy, and I have animated my smiley face guy, and he's doing something periodically. If you watch this motion, you can see kind of a figure 8 pattern. And as long as it repeats over and over again, that would be an example of periodic motion. I'm going to use my stopwatch to determine the period. So I'm going to start when the smiley guy is over there on the left. So next time around, here we go. Actually, I'm going to wait one more time. Here we go. Start. Stop. So I got 3.09 seconds for that to occur. Did you time it? You might time it yourself. You could start at a different spot. Would that change the outcome? I'm going to reset my timer. I'm going to start now when my smiley guy is up here on the upper part on the right. So just listen. I'm going to start right there next time around. Here we go. Start. Stop. That time I got 3.04. It doesn't matter where you start as long as you wait for one complete cycle. So I didn't time this perfectly. Of course, nobody can really do that with a stopwatch, but I was very close to the time that it's taking, which should be right at 3 seconds, which is what it's programmed to do. Let's look at another example. So here, my smiley guy is doing the worm, it looks like. So this hopefully would be pretty straightforward. Should I time one worm, say going to the right, is the worm coming back to the left different than the worm going to the right? Well, in physics terms, yeah. I would want to go over and back. So you might be tempted to just go one way, but it needs to come back to the starting point. So if I were going to time this, I'm going to do this one. Here we go. Start. Stop. And I got about 4 seconds for that. And that's about right. So here's another example of periodic motion. Now, we're going to look at one more. You ready? Get ready with that stopwatch. Ooh. Yikes. This is going to be kind of hard, right, to time this. Well, there is a way to do this, and probably the best thing to do here, you might figure this out on your own. Notice this time it says find the period and the frequency. So frequency is often used for things that are moving more rapidly. There's no hard rule about that, but anyway, we're going to find both the period and the frequency. And the best thing to do here would be to time multiple times around and then kind of find an average in a way. So what I'm going to do is I'm going to start counting. I'm using my stopwatch here. I'm going to go 3, 2, 1, 0, 1, 2, and start counting like that. I'm going to start on 0 and end on 10. So I'm going to time 10 cycles. So here we go. 3, 2, 1, 0. Wait, that didn't start. I got to use my stopwatch. Here we go. 3, 2, 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so timing 10 times around, I got 4.02 seconds for 10 cycles. Now, what would I do with that to figure out the period and the frequency? We need to go back to the definition. One of the most important things to know about period and frequency is the definition. That's true for lots of things in physics. Definitions are important. So if I wanted to find the period, and I know that it took 4.02 seconds to go around 10 times, I need to use that information to find the time to go around 1 time, and that would be the period. And hopefully that's pretty straightforward. If you take the total time to go around 10 times, 4.02 seconds, and divide by 10, that would give me the time for 1 cycle. So that would be telling me, oh, there are 0.402 seconds per 1 cycle. Now, we don't normally write down the word cycle because that's implicit in what we're finding. We're finding the period, and by definition, that's the time for 1 cycle. So our correct answer here for the period would be, the period of this motion appears to be about 0.40 seconds if we round off a little bit. Uncertainty in our numbers. Now, what if you want to find the frequency? Well, the definition of frequency is flipped around, and so would the calculation be. So frequency is not the amount of time per number of cycles, it's the amount of number of cycles per amount of time. So we're just going to do kind of the same thing, but flip those numbers around. So now we're going to take 10 cycles and divide by the number of seconds. And that's going to give me a certain number of cycles per second. Again, the word cycle is not really a unit, so we don't necessarily treat it like a unit. It helps in your mind to think of it, okay, we're finding how many cycles per second, but I normally would write it as just 1/seconds. But 1/seconds is equivalent to this special unit we call the hertz. So I'm going to say my final answer here, the frequency of that motion that we were watching is 2.5 hertz. And what it means is 2.5 cycles per second. Those two quantities, period and frequency, are reciprocal quantities. The definitions are reciprocal. Mathematically, they are reciprocal. So if you think about what we just did, we found the period and the frequency. Well, if you take 1 over the period, that would give you the frequency. So 1 divided by 0.4 is equal to 2.5. Or if you took 1 divided by the frequency, 1 divided by 2.5, that would give you the period, 0.4 seconds. So that sometimes is helpful to be familiar with that frequency and period are reciprocal quantities of one another. Here is a real-world application, you might call it, how frequency and or period is illustrated by the gauges in a car. So the one on the left shows how many RPM, and that is called the tachometer. The tachometer is showing you how many revolutions per minute the crankshaft of your engine is undergoing. And that's usually abbreviated RPM. And you'll see that one fairly often. So I want you to be familiar with RPM, revolutions per minute. So let's turn this into a little example problem. Let's suppose that you're going down the road and your tachometer shows 2,500 RPM. What would be the period of each piston in the engine? What I would do if I were you is think about this quantity. 2,500 RPM can be converted to RPS, or revolutions per second. Write it like this and do a unit conversion. 2,500 revolutions all divided by minutes, and then factor analysis, factor label method, whatever you want to call it, we can convert that into revolutions per second by dividing by 60 seconds. If we do that, then the minutes are going to cancel, and I'll get the number of revolutions per second, which would be 41 2/3 revolutions per second. And then once I have that, I could use my reciprocal relationship that we just mentioned. Well, the period would be 1 over that. So 1 divided by 41 2/3 would give me the number of seconds for 1 revolution of the crankshaft, and that would be the period for 1 piston to go up and down, which is kind of wild to think about. So when you're going down the road, these pistons are moving up and down very rapidly. Up and down in 2/100ths of a second would be a typical value. And that would be a type of periodic motion. Now, one important application of periodic motion is a special case of motion that we study in physics called uniform circular motion. Uniform circular motion would look like what I have shown in this animation. Here we have a little ball moving around in a circle, and it's uniform in the sense that it has a constant speed. So I guess that may not be entirely obvious, but in physics, it is a common expression. Uniform circular motion, what we're referring to with uniform is an object that has a constant speed moving in a circular path. For Physics 1, we want to be familiar with the kinematics of that, and the rest of this video goes over the kinematics. But you know what? It's the same definitions. You already know kinematics. So I've turned this into trying to make this a little bit more interactive, kind of a little set of multiple choice questions. If you remember your definitions, you should kind of already know what to do. So let's see. Let's suppose that we're only focusing on a small piece of the motion. And I move part way around the circle. I could draw some arrows. I could kind of shade in this green arc and then ask a multiple choice question. The orange arrows are position or displacement. The blue arrows are position or displacement. The green curve is displacement or distance. Well, you should already know that based on your definitions that you learned previously. So the point I'm trying to make here is that it's a new topic. Okay, I've got circular motion, but the definitions are always the same. So what are you going to pick? I hope you picked this one, B. It would make the most sense to say, okay, the orange arrows must be position, the blue arrow is displacement, and the green arc would be the distance. And that makes sense because of the definitions. Position is an arrow showing where something is relative to a point of reference, and the center of the circle would be an obvious choice for the reference. Remember, displacement is net change in position, which is a vector quantity. It's just a straight line from wherever you started to wherever you ended. And then distance is the length of the path traveled, which for circular motion would be an arc length. All right, let's look at another question here. From kinematics, hopefully you recall that if you have a constant speed, you could find the speed by dividing distance by time. So if that's the case, which of the following equations would give the speed of an object in uniform circular motion? Pick your answer and see if you get it right. Here comes our answer, B. Why is B the correct answer? Well, I hope you picked B. Distance per time. For circular motion, the distance is a circumference, and the circumference of a circle can be found by 2 pi r. And we already talked about this special symbol that capital T represents period. So we can use this little formula, handy little formula, for finding speed when an object is moving in circular motion. This would be give us the speed for a constant speed. If you had a changing speed in a circular path, which would be possible, this would at least be an average value of speed, just distance per time. So hopefully pretty obvious where that comes from. Now, one more thing to talk about as far as our concepts go. How is velocity for circular motion different than speed for circular motion? Well, as you well know, velocity is a vector, and that's what makes it different. Velocity includes a direction. And if we want to specify the velocity in circular motion, we need to specify the direction of the vector. So here's a fun question for you. The velocity vector would point in one of these 3 directions, either toward the center of the circle, away from the center of the circle, or tangent to the circle. Think about what velocity is, rate of change in position, and how it has been applied previously in lots of examples you've seen. What do you think the answer would be? See if you pick this one right. It's one of those 3. Okay, here we go. C, tangent. The correct answer is tangent to the circle. I have an animation of that. Looks like this. So now we're showing this velocity vector, which would go with the object and always be tangent to the circle. So hopefully you remember that word from geometry and mathematics. It would be a straight line touching the circle at one point. Also would be perpendicular to a radius drawn to the point where the object is. So velocity for circular motion is always tangent. That's actually also true even if it's not uniform circular motion. It would also be true for an object moving in a circular path with a changing speed. It would still be a tangent velocity vector at all times. Okay, now last thing in this video is an example problem. So here's a fun one. Look, I have an animation. Here's an example problem. A turntable rotates at 33 1/3 RPM. Do we have any vinyl fans out there? So if you have a record player at home and you have some LP records on vinyl, 33 1/3 RPM is the standard rate for playing those records. So let's imagine it happening. Set up this animation carefully. This is actually the correct rate. If you really want to, you could time this, and you should find 33 1/3 RPM for that turntable I'm imagining here. And then I have two objects, a frog and a duck. The frog is 9 centimeters from the center. The duck is 18 centimeters from the center, we might imagine. So how do I find the speed and the period? We're going to do that together. I'm going to freeze the animation and move it over here to the side to give me a little room. So let's start with period. 33 1/3 RPM is a quantity we already saw. That's a value of frequency. So I would do 1 over frequency to get the period. 1 minute divided by 33 1/3 revolutions is the reciprocal of 33 1/3 RPM. And if I do a little unit conversion, multiply by 60, I would get the period, 1.80 seconds. Now, which object would that be true for? Let's watch our animation one more time. Well, if you think about it, if they're both on the platter, they're both on this turntable, they would both finish 1 revolution in the same amount of time, 1.8 seconds. So this would be the answer for either object for the period. But then we're asked to find the speed. Speed for circular motion, if it's uniform, which it would be in this case, would be 2 pi r divided by the period. Our two objects have different radii. So our frog is sitting here at 9 centimeters. That's 0.09 meters. Divide by 100 to get 0.09. And then calculate R1, 2 pi R1 over period. And that would give me a speed for our frog friend here, 0.314 meters per second. But our duck is faster. Why is the duck faster? The duck is faster because it's farther out. It's moving a greater distance in the same amount of time, and therefore it has to have a greater speed. So the speed of the duck, 0.628 meters per second, would be the correct answer for this problem. Summarizing, each object has the same period, 1.8 seconds, and then our two objects have different speeds. In this image shown here, I've also illustrated the way the velocities would be pointing at that particular instant in time. Think about the two speeds being different. Let's watch our animation again. If you just watch the duck and watch the frog, does it make sense to you that the duck is going faster? Does it look like it's going faster? Imagine being on a merry-go-round. Wouldn't you be going faster if you were near the edge? You would. Okay, so I hope that this has been a helpful video to introduce a few ideas to you. I'll see you again soon.